How much room have I got? A little bit. All right. G'day everybody. Thanks for coming. So this is kind of the first talk I've really given actually since March of 2011, that Getting in the Shape of the Sport of Data Science talk, which I planned at that time to speak for about an hour, and I remember I think I ended up going for 3, so I'll try and not do the same thing this time. In fact, I might even get my phone out so I can keep an eye on the time, because I think something about going to the pub afterwards was mentioned. All right. How many people have seen either in live or on video that Getting in Shape of the Sport of Data Science talk? Yeah, a few of you. Cool. So at that stage, it was kind of weird, right? Because I had just come off the back of doing 2 startups. One was an email company called Fastmail, which was, I think, pretty much the first kind of consumer IMAP provider. So, you know, the first company to try and provide synchronized email for consumers. And another startup called Optimal Decisions, which was an insurance pricing, insurance analytics startup. And, you know, the weird thing is, after running your own thing for 10 years, you kind of assume that you've lost all skills yourself because you spend all of your time getting other people to do shit for you. So after I sold the second of those startups, I came along to an R Meetup group and started saying to people, how do I kind of, you know, learn R properly and, you know, develop my skills? And someone said to me, oh, you should try a Kaggle competition. They're these predictive modelling competitions where you can enter and you can like put in a new entry every day, and hopefully you get better over time, and they're a really good way to learn. I thought that sounds really cool, but also really terrifying, because again, kind of after 10 years of telling other people what to do, the idea of those people discovering that I was actually no good at what I was talking about was really scary. But I thought, no, damn it, I'm going to sign up with my real name. None of this, you know, user123 business. I'm going to sign up with my real name, and if I'm crap, then I'm crap. So be it. I've sold the company now. Doesn't matter what anybody thinks. So I did. Yeah, it was kind of really weird. It actually turned out I was pretty good at this stuff. I actually won the first competition that I entered, and then I came second in the next one, and then I won the next one. And so by the time I came back to the R Meetup group, the people who kind of said, you know, how do I get started with this R stuff, kind of said, well, actually, it seems like you know what you're doing, because by that stage I was the top of the global rankings for Kaggle competitions. So that was totally surprising for me. I had no idea that I could do that more effectively than other people, because I have no technical training myself, and I thought, you know, you had to be like a mathematician or something to be good at this kind of thing, and it turns out you just need to be bloody minded enough to not give up, basically. So tenacity turned out to be the trick, I guess. So then, yeah, I'm just doing this. Hello, great. So then I kind of said, all right, well, I guess I'll come back to this Meetup group and talk about how I do what I do, since it seems I can do it quite well. So that was what that talk was, and it was really just a brain dump of, you know, everything that I thought I seemed to do okay at. The last half of that talk was actually about random forests. How many people here are familiar with random forests or know something of what they are? Oh, okay, that's interesting, less than I would expect. So if I just hit this thing, wiggle around, no, okay. If I talk like this, is this enough? Can you
when it comes out, the one at the back still works, so it's all right.
The one at the back still works, okay, so you can still hear me okay?
Oh, we can.
Okay, great. No worries. I can still hear you as well. Okay. Cool. Where was that? Oh yeah, that's all. Okay. So I talked about random forests because it's a particular machine learning algorithm, which I thought was just a fantastic algorithm. It's been around since 1999, but at that stage, not many people had heard of it. So after I gave that talk, and then I started telling other people, you know, it kind of gets like, oh, you're talking about Kaggle, how do you do what you do? And I started saying, oh, random forests, random forests, random forests. Next thing I know, everybody's doing random forests, and actually now, you know, a number of startups appeared in the next year or two focused on doing random forests, and I met some of the founders, and all of them said, yeah, I did it because of what you said about doing Kaggle competitions. So it actually turns out that that talk had quite a bit of impact. Yeah, so here I am back again, and like actually at this point, whereas last time I was doing a tech talk in Melbourne a few years ago, I really felt I had no idea what I was talking about, and it was really just sharing my kind of personal experiences. As a result of spending a few years at Kaggle and some time in Silicon Valley and talking to a lot of the world's best data scientists through that experience, I actually think I vaguely do now know what I'm talking about. So I wanted to kind of give you a sense of, I don't know, some of the things I guess I've learned over the last couple of years. So I give this background in order to, because I actually come here not with a specific talk prepared, but I want to make sure I do a talk that suits you guys. So that's why I'm starting with a background. So broadly speaking, yeah, so I'm a guy with a kind of a non-technical background who started a couple of startups, came across Kaggle, entered some competitions, did well, met the founder of that company by accident. Turns out he was another member of the Meetup group, and somebody introduced me, and so I became the first angel investor in that company. And as the first angel investor, I actually received the email that Phil sent to Anthony saying, you know, a lot of these guys on the site aren't statisticians, because Anthony came to me and he said, Jeremy, is that true? And I said, well, I'm certainly not a statistician. And Anthony said, oh, well, what do we say then? And I said, well, what about data scientist? And I'm like, oh, okay, let's be data scientists. So that was how that ended up on that website. So, you know, it was kind of funny because I started volunteering for bits and pieces. You know, I helped tune the database, and I ended up kind of actually rewriting the whole website along with one other guy. But it's just kind of volunteering. One thing led to another, and next thing I knew, I found myself in Silicon Valley, basically pitching to venture capitalists this company. I told Anthony that it was probably a waste of time because, you know, we're just some little Aussie startup, who in America is going to care about that? He thought maybe they would. Turned out they did, to the tune of $11 million. So he was right, I was wrong, and that was why I ended up moving to Silicon Valley, because at that point the investors were like, well, if we're giving you $11 million, we want you in kicking distance. So Anthony and I moved over there. And yeah, I've got to say that's been a really interesting experience. It's a very different world over there for an entrepreneur, particularly a data-driven entrepreneur. You know, really, the vast majority of the world's top data-driven startups are based in the San Francisco Bay Area. So that's a bit of my background. I guess at Kaggle, what I learned a number of things. One thing I discovered was a small number of people won a very large range of competitions. So like one guy would win like competitions across multiple different domains, using multiple different types of data, using multiple different types of problem area. And so it wasn't so much that these things were being won by specialists, but quite the opposite. And like I'm a good example of that. I actually intentionally only entered competitions in industries I'd never worked in, with problems I'd never worked on, in data types I'd never had any familiarity with, because it kind of maximizes your opportunity to learn. The second thing I discovered was that these data scientists basically use just like two algorithms nearly all the time. For the first year or two, it was nearly always random forests or something else from that class. So for those of you that are more familiar with machine learning, you would know, for example, gradient boosting machines are a very similar algorithm. In the last year, increasingly, people have been using deep learning to win these competitions. So I discovered it was a small number of people using a small number of algorithms. It actually got to the point kind of mid last year where I started thinking, gee whiz, you know, running competitions to find out the best solution to this problem seems kind of weird, because I already know it's going to be one of these people, more or less, and they're going to use one of these two algorithms, more or less. And the process that people use to win these tends to be pretty well defined as well. It's basically lots of brainstorming, lots of creativity, just trying as many things as possible, not doing any filtering yourself, but letting the algorithm do the filtering for you. So Phil's had a lot of success in data mining / predictive modeling competitions, so you would know what I mean about this kind of process that we all follow, right? Yeah, so I ended up leaving Kaggle in October, and in about a month's time I'll be launching my new startup, which will be focused on building the software which kind of basically puts these algorithms and processes in place and makes them available for anybody, regardless of whether they code or not, regardless of whether they're statisticians or not, makes these kind of algorithms available to everybody. So, with that background, let me tell you guys what I could spend some time talking about. And I could do a number of these things. I could spend some time talking about my experiences of building a venture-backed startup in Silicon Valley and what that took, and maybe some differences to doing bootstrap startups in Melbourne, which is what I did first. I could talk a little bit about this newish algorithm called deep learning, which I actually think is going to be more important than the internet or the computer. And I could tell you a bit about what it is and what the impact might be on the world. I could talk more about applied random forests. This is still the algorithm which, at least in industry, is the most effective day-to-day used algorithm. I could talk a bit about why it's important and how it's used in real life. Well, finally, I could do a more deep technical dive into deep learning and talk about how actually does deep learning really work at a kind of more technical level, not with any mathematical equations or whatever, but actually getting into some of the detail. So let's see a show of hands for people who would be particularly interested in hearing about the kind of the venture-backed startup story. Okay, not surprising, that's good. So we're here for data science, not for startups. Who's, what did I say? So who's interested in hearing about kind of high-level deep learning, what it is and the potential impact on the world? Okay. Who's interested in kind of applied random forests? And who's interested in a kind of deeper technical dive into deep learning? Okay, that's interesting. Now, am I missing something? Is anybody here hoping very much to hear about something totally different? Just let me know. Yeah?
I'd be curious to hear some case studies about how data science is actually applied and extracted in the research.
Okay, yep, I can do that. Anything else?
The future of data mining competitions.
Future of data mining competitions? Okay, cool. I think I can put this all together then into something. I actually have a presentation about deep learning which covers a bit about what's happening in data science right now. So maybe we'll start with that. And time permitting, I'll go a level deeper into talking about how it actually works. Okay, so let's actually start with the. Actually, I can get you this. Let's start with a bit with kind of. I'm more interested in talking about machine learning than data science, I've got to say. So, data science, broadly speaking, is the science of how you get insight out of data. There are a number of pieces to that. You need to collect the data, you need to store the data, you need to make the data available in a kind of quickly and in a convenient format, right? And honestly, a lot of people, when they talk about investing in data science, spend all of their time on those three things, right? So I teach at a number of places. One of them is Singularity University. Singularity University is where a lot of the world's top executives of the world's largest companies come to learn about, what's the latest stuff in technology. And so I have a lot of opportunities to interview people and find out what are you doing with data. And the answers tend to be things like, oh, so much, I just spent $40 million on a Hadoop cluster. Right? Now that's the first three things, right? That's collecting and storing and making data available. I find that the boring bit. It's the plumbing, it's necessary, but people look after it, it's fine. What sits on top of that is getting value out of the data. And so getting value out of the data can come in a number of ways. Broadly speaking, it could be about extracting insight from data. That can be done, for example, using traditional business intelligence tools. So we're talking Tableau. Is the Tableau meetup still running in Melbourne? Yes, it is. Okay, so that's one of the top options. Perhaps the top option I'm aware of for quickly slicing and dicing and getting pictures out of data. But there's a lot of stuff in that area now. There's stuff like Platfora, and of course there's good old Excel pivot tables. But this whole area of kind of visualization, reports, charts, and so forth. I think that's very interesting and very useful, but my issue with that is you have to come with the hypothesis, right? Tableau doesn't tell you what to look at, right? You tell Tableau what you want to look at, or pivot tables, or business objects, or SQL. So there's a bit of a lack of intelligence there on the part of the computer, which is fine. If you're going in saying, I think the answer is X, I just want to prove it, that's a great way to do that. Or even it could be X, Y, or Z, quickly try out a few options. My issue is that I want to know about the things I didn't think of, right? Or the hypotheses that I should have been asking about. And this is where machine learning can be incredibly helpful, because machine learning is the piece which is asking the computer to provide some of the intelligence for you. And it's not a replacement for visualization, it's not a replacement for human interpretation, it should be an addendum to it, right? So at the opposite end of Tableau is stuff like Google Prediction API, prior knowledge, Big ML, stuff like that. These are companies or products which you feed it data and it runs some kind of model and it feeds you back scores, right? Probability of this loan defaulting, or probability of this insurance customer claiming, or probability of this customer buying the latest Miley Cyrus CD, or whatever. So that's a kind of a black box scoring model, which I think a lot of people think of machine learning, they think of that, right? And I do want to say that's not what I'm talking about when I talk about machine learning, or at least not necessarily. My interest lives right in the middle, which is using machine learning to help you find the interesting insights and help you leverage them. So, all of that is data science, including the bit after, which is where you take the models that you built and put it in production, and there's all that stuff as well. But the bit in the middle, which is the finding the insights and leveraging them and creating value, is the bit I think is the most interesting. So that's the bit that I want to talk about, and it's also the bit, I guess, if I'm good at anything, it's at that bit, so I should focus there. So, who knows who this is? I don't think anyone would. You should. This is Arthur Samuels. He invented machine learning. He is famous for being an extremely bad checkers player. So bad, in fact, that he was not able to program this computer to play checkers effectively. He couldn't play checkers effectively himself, and he certainly couldn't tell you the rules for how to play checkers effectively. So because he's very bad at playing checkers, but because he decided he wanted to create a computer program for playing checkers in 1956, he had to think creatively. So what he did was he set up something where the computer played against itself at checkers. And he basically described at a high level the kinds of levers that you could pull, the kinds of different styles of play that you could have, and what the numbers were for each of those kind of different rules of the kind of things you could do, or the kind of ways you could score a board, or so forth. So, in machine learning sense, we'd say he parameterized the problem. He figured out the parameters which, if you set all of these numbers, you end up with a particular way of playing checkers. So then, having got the computer starting to play against itself, playing checkers, watching how well it did as it tried changing the parameters, tried changing these numbers, he then basically stuck an optimization algorithm on top of that. So anybody who's interested in machine learning absolutely has to understand optimization, because at the end it's basically all optimization plus linear algebra, right? So even me, with no technical background, they're the two things that I understand, because you absolutely have to. So he put an optimization algorithm on top of this, saying, try lots of different parameters to find out the best set. And eventually he ended up with a program that could beat him at checkers. That's not bad for 1956, right? In fact, the computer kept getting better and better. And by 1962, it had beaten the US state champion at checkers. So, in 1956, Thomas Edison, who at that time was running IBM, which is where Arthur Samuels was working, announced to the market that they had invented a program that could play checkers. And in fact, the program that could play checkers effectively kind of programmed itself. He described this approach that became known as machine learning. On that day, because of that announcement, IBM's share price increased by 15%. So, machine learning also has a long history of having huge commercial impacts. In some ways, the funny thing is how long it's taken, right? Because Arthur Samuels actually made two predictions in a paper in the early 60s. Prediction number one was, and he was the first guy ever to say this as far as I know, very, very crazy idea at the time, every person in the world could have their own computer one day. The second prediction he made was that within 20 years, very few people would be programming their computers. Instead, computers would be learning to do the things that were being asked of them. So the second piece has taken a lot longer, right? But actually, in my view, it's happening, right? So, where are you seeing machine learning right now? Well, if you search Google, before Google existed, the big guy in finding stuff on the internet was Yahoo. And Yahoo was a company that had a whole bunch of editors, people that surfed the internet, finding interesting websites and manually putting them into a hierarchy, and that was Yahoo. The world's largest website by far. I think they had something like an 80% market share at that point. Google came along and replaced all of that with an algorithm called PageRank, which is effectively a particular kind of machine learning algorithm. Again, it's a particular way of actually doing optimization, basically. And so every time you use Google, you're basically using a machine learning algorithm. In fact, many or maybe even most of Google's coolest shit is being run by machine learning. So the ads you see in AdWords is basically a machine learning algorithm figuring out what ads to show you will maximize their revenue. Google Translate is a really interesting example. It has not been programmed with any rules about how language works or about how you translate from one language to another in terms of vocabulary or grammar or anything like that. Instead, what Google did was they scraped tens of millions of websites that had already been translated by humans. And then they created a machine learning algorithm which effectively, this is simplifying things a little bit too much perhaps, found the correlations between pages that were in different languages. Here's the English version, here's the Spanish version. And effectively, having done that, they then run that set of correlations backwards. So when you say, here's my English site, please translate it into Spanish, they kind of rerun that back again, right? So this is called statistical language translation. And today, of the 5,000 language pairs that are tracked, for 4,999, the best known algorithm is a statistical language translation algorithm. The 5,000th, by the way, is English to Japanese, which is currently a hybrid approach, is the best. If you ring your insurance company, get a quote, it's pretty likely that they're using some machine learning to decide what price to quote. So I spent 10 years working in that industry, helping a lot of the world's largest insurers figure out how to optimize their pricing using machine learning. And similarly, in banking, if you get a loan, the decision as to whether or not to give you credit or not is probably being done with the help of some machine learning. That last example actually is particularly interesting to me because about 20 years ago, I tried to get one of Australia's big finance providers to switch from using manual lending auditors to make that decision to using an algorithm. And so I effectively back-tested my algorithm, and I said, look, it would have been more profitable for you to have used that algorithm than to you to have used those people, because at that stage it was all done with people. And so the head of product at that time said, that's just ludicrous. You know, these people are expert, trained human beings who can see the subtle things in a loan application. And there's just no way that a computer program or a mathematical function could do that totally human thing that these experts are doing. Like, I just don't believe it. And so they didn't implement this algorithm. A lot of other people did, and the particular company I worked for 6 years later was bankrupt because they had failed to correctly predict their loan losses. And today, every company in the world uses at least statistical algorithms, if not machine learning algorithms, to decide who to advance credit to. I mention this because still today, every single industry that I talk to and say, you should consider replacing these people doing this thing with an algorithm doing the thing that the people are doing, the answer is always the same. You know, you eggheads just don't get it, these people are special and unique flowers and they can't possibly be replaced with a machine and blah, blah, blah. And inevitably, eventually, Google or Amazon comes along and does replace them with a machine, and everybody else goes out of business. So it's kind of tough trying to advance machine learning in this environment where the vast majority of the world's management and executive teams don't get it. They don't know how it's transformed other industries. They don't know that it's going to kill their industry too. And so the general belief, at least in Silicon Valley amongst venture capitalists, is that it's pointless trying to get big companies to change. You should found a startup and do it yourself, which is, you know, interesting advice, I think. So this is kind of where we're at with programming at the moment, is that it's this complex, difficult thing to do, where we have to write all of these rules and loops and so forth. But in some areas, slowly we're replacing some amount of that with machine learning. I actually found a really good example just a couple of days ago. I'll just see if I can find it. Alright, let's have a look. What would I search for? Color, contrast, neural network. I think that'll do it. Yes. Check this out. So here's a good example, right? Deciding how to determine whether or not a pair of colours is good contrast for human perception or not is actually quite difficult. And there's years of research that's been done on this, and as a result of those years of research, you know, and kind of implementations of that in software, we now have libraries you can kind of download or whatever or subscribe to that will handle for you deciding how much contrast human visual perception will believe there is between two colours. The guy who created this page didn't do any of that. Instead he said, just give me some examples. Which one of these can you read more easily? So at least on my screen it's this one, oh close, maybe this one, definitely that one, that one, that one, that one, definitely that one. Okay, so I've given it a few examples, and so what it's going to do now is, rather than use this kind of visual perception model and run lots of rules and stuff, it's just going to train a neural network which will use my labels as the thing that it's trying to find. Okay, it's done. All right, so now it's going to show me some examples of pairs of colours, and it will tell me whether the neural network I trained thinks that the best colour for the front would be white or black on the left, and on the right it's going to show me what the official formula says. So my neural network is the same as the official formula for this colour. For this colour, my neural network is different to the official formula. And interestingly, I can actually see the one that my neural network likes better. So in this case, the neural network has beaten the formula. So you can see here effectively what's happened is this little demo, it's run entirely in JavaScript, it took 50 milliseconds to run, has allowed a programmer here to replace a whole years of research and manual programming with a machine learning algorithm, in this case a neural network. I should mention, nowadays when people say neural network, they almost always mean a deep learning neural network. So deep learning just refers to a neural network with lots of layers. So I find this really exciting. So I've got a couple more examples here of kind of how machine learning is currently used. So LinkedIn's people you may know is like creepily good sometimes, and it's good because people didn't program the rules into that, it's learned them from data. Even things like the Google self-driving car, figuring out how to write the rules to tell a car how to drive based on LiDAR sensors and blah, blah, blah. It's like, there's just no way any human being could do that. So inside this is a whole lot of machine learning algorithms. And this is really a big part of the reason that we now have a self-driving car. And 10 years ago, all the world's experts said it would be impossible, at least in our lifetime, for us to ever build one of these things. And so the final example of kind of machine learning that's currently applied, of course, is Watson winning Jeopardy. So this is an example of an actual question that was asked. Can you guys see this okay, or should I turn the lights off? You can see, okay. So this idea of kind of being able to understand language well enough to answer questions like this, when I studied linguistics. Pardon me? So this question is, the ancient Lion of Nimrod went missing from this city's National Museum in 2003, along with a lot of other stuff. So that's an example of a Jeopardy question. And so Watson beat the two best players after have played the game. So not just any random humans, but this is Ken Jennings on the far left here. So the reason it was able to do this is because they were able to do a lot with machine learning. For example, they had something that was a lot like a deep learning network, effectively read the entirety of Wikipedia. Not with rules that kind of said, if you see a word in this grammatical construct, it means that this has happened, and manually creating a knowledge base. No, it actually read it in a much more fuzzy sense. And I'll go into that a bit more shortly. Okay, so that's kind of an answer to the question of like, what are we using machine learning for now? Which is a bit different to the question you asked, which is what are we using data science for, but I get the microphone so I get to interpret it how I want to. This is the start of my what's happening next piece, right? And this is a picture from an academic paper. These things are breast cancer image slides. And there are little green arrows pointing at areas of what's called mitosis. Mitosis is the worst part of a tumour, basically. And these are the bits that a pathologist wants to find. Turns out it's really hard to find them. It's really hard to decide from these images what's a mitosis and what's not. So what happens is when they're doing this properly, they send these slides out to 4 pathologists independently, and each one marks them up independently, sends back the results, and effectively that's a vote, right? And so whichever ones get the most votes are the areas that they decide are areas of mitosis. These marked up images, as marked up by a panel of 4 pathologists, became the data source for a machine learning competition in 2012. And the winner of this competition, their algorithm was more in agreement with the panel of pathologists than any individual pathologist was. Right? So this algorithm, which is not in industry yet, this is just from research, is better than any pathologist at doing breast cancer screening. So this is surprising, because traditionally looking at stuff is something that people do better than computers, right? And this is not just looking at stuff, this is people who spend decades learning how to look at this particular kind of stuff, right? So this was quite a big deal. In fact, 1 year earlier, in 2011, was the first time that an algorithm had been developed that could look at stuff better than humans in general. That was a 2011 competition in Germany for trying to create an algorithm that could recognize street signs. And in this German competition, the humans had about a 1.3% error rate. You know, sometimes the signs were very dark or very blurry or whatever. The computer, the winning algorithm in the competition had an error rate of 0.5%. Right? So, to give you a sense of how fast this is moving, we went from 2011, first time ever that a computer was somewhat better than some people were doing some things, to better at trained experts at doing something really hard. So that's just 1 year of development. Another in the kind of the sense of what's coming out of academia, since I have a real internet connection, I can show you this one. So this is some work that comes out of Stanford. Stanford sentiment analysis. Should do. There we go. Oh, what just happened? Okay, let's try that. Right, click. So sentiment analysis is something that's actually quite difficult for machines, right? Which is the question of trying to decide whether a sentence is positive or negative in sentiment, right? It doesn't sound like it should be that hard, but actually think of a sentence like this one. This movie doesn't care about cleverness, wit, or any other kind of intelligent humour. You know, to a kind of standard algorithm where you like count up the number of happy words versus sad words, this sounds like pretty happy, right? And it requires a reasonable level of understanding of how human language is structured to recognise actually this is a negative sentiment sentence. This is in fact so hard that the actual underlying grammar of how language really works to decide like this has still not been fully specified. So a lot of you will know of Noam Chomsky. Noam Chomsky was kind of the guy who did the most to develop this idea of universal grammar. We're still a long way from actually understanding fully how the grammar of language is fully specified. So there's no way we could write the rules to decide if this is actually a happy sentence or a sad sentence. And yet this is an algorithm coming out of Stanford that if I submit this sentence, hopefully it gets it right. Here we go. Here is this sentence has been parsed into a parse tree. So intelligent humour, any other kind of intelligent humour, and this phrase here is positive, and this phrase here is positive, and this phrase here is positive, but overall the whole sentence is negative. Right? Now, one of the interesting things about this Stanford algorithm, well, first thing to tell you is it's only 5% less agreement with humans than humans are with each other. Right? So humans are about 85% in agreement about whether these kinds of sentences are positive or negative. This algorithm is about 80%. So it's not quite up there with humans, but it's pretty damn close. Even the way it's actually parsed out this into a parse tree was done with no manual programming of rules. This was done entirely with machine learning, even to recognize what the structure of the sentence is. So not only are we now better than humans at certain classes of looking at stuff, we're nearly as good as humans at understanding fairly subtle language. And we can now even combine these two together. This particular algorithm is in a paper that was just published 2 weeks ago, so we're now right up to kind of the very best we have. On the left-hand side are some images. This is a small selection of thousands of images that were used in the data set for this paper. On the right is a small subset of the thousands of sentences that were used in this paper. This is demonstrating a machine learning algorithm which attempted to match each picture with one or more sentences that were a suitable description of the picture. And here it's put in green the ones, and this is actually selected from thousands, which it thought were the best best match. So again, this has been done using machine learning, and what it's done is it's taken these pictures and run these through an algorithm to try and kind of come up with an understanding of what it's a picture of, turn the sentences through an algorithm to try and decide what the sentences are about, and then found some way of matching the two things together. So we're now at a point where not only can we use algorithms to understand pictures and to understand natural human language, but even now to integrate these things together pretty damn effectively. So one interesting feature that I want to point out is that everything that I've shown you from Watson on is actually all based on just one algorithm, and that one algorithm is deep learning. So I haven't been showing you the results of all kinds of specialist machine learning algorithms, but of just one. Deep learning today is actually the best algorithm in the world for not only everything I just showed you, but also for reading cursive handwriting, for recognizing human speech, and this one here, which was a Kaggle competition won by deep learning, for predicting which drugs will be toxic, for doing database completion, so basically finding errors and missing features in databases. Every one of these areas is the world's best algorithm today is known to be deep learning. So this is why this is an unbelievably important algorithm. So this particular competition, which was actually run on Kaggle, where I used to work, was the first kind of general purpose machine learning competition that was won by a deep learning algorithm. So this was a competition about which molecules will turn out to be toxic. The guy that won it was Geoffrey Hinton, who kind of invented deep learning, and his team. It was actually mentioned in a front page article in the New York Times as part of a general article about the impact of deep learning. The other thing they showed was, actually maybe I can show you this cool little demo. I'm not sure how else it's going to work, let's see. Okay, let's see if this works. So the trick is whether putting this microphone next to my speakers is actually going to work correctly or not. And also whether let's try this. Okay. Oh, in fact, there's no sound coming out of my computer even. Oh, I don't know why. Hang on a sec. Let's try sound. I bet it's using HDMI. Playback. Yes, it is. Set default. Okay. Try this. Okay, never mind, that's not going to work. So, were you able to hear what he was saying, you would find out that he's describing that as he's talking, you can see the transcription in English appearing on the left. You can see the transcription on the right appearing in Chinese. That's all been done automatically in real time by machine learning algorithm. And then he describes how they then trained an algorithm to listen to his voice and to translate his spoken English into spoken Chinese with his original voice modulation in real time. And the thing that makes the demo particularly impressive, were you able to hear it, which you're not, is that he's doing this in China, and as soon as the machine starts translating the spoken to spoken Chinese, the crowd basically breaks out into spontaneous applause. I think he actually got a standing ovation, which, believe it or not, does not normally happen at machine learning conferences. But feel free to prove me wrong at the end of this talk. Totally spontaneous applause. So if you... so this guy's name is Rick Rashid. So I just... I was going to say Googled for, but I guess actually I'm being here. Microsoft Research, Mandarin, Rashid. And go to about 6.5 minutes to get the cool bit. It's all pretty cool. So this New York Times article kind of covered that as well, which is why you see Rick Rashid at the back there. So one of the interesting things about this is what they mentioned about Geoffrey Hinton's team, which is that no one in his team actually had any specific knowledge about how the molecules bind to their targets. That's actually kind of the world's biggest understatement. No one in the team had any previous training in biology, life sciences, molecular biology, pharmaceuticals, anything. They were all machine learning researchers, and in 2 weeks they created the world's best chemoinformatics algorithm, better than anything Merck had created, anything anybody else in the world had created, with a relatively small set of data. So it kind of seems like every time someone points deep learning at something now, it turns out to be the world's best thing. And I particularly know this to be true because the co-founder of the startup that I'll be announcing in a month or so is a guy called Richard Socher, who is the guy who invented basically the whole field of applying deep learning to natural language. He published 10 papers last year, which is very unusually large, particularly for someone who has not yet even got his PhD. And he basically said the reason why is every single time he points deep learning at any long-standing unsolved NLP problem, it solves it. Right? So it takes 2 weeks. It's like, oh, turns out it's best at that. Oh, turns out best at that. Blah, blah, blah. So he has paraphrase detection. He can figure out whether 2 sentences are kind of about the same thing better than anybody else. The Stanford sentiment analysis work was his. The linking up the images to the sentences was his, and so forth. So there's a small number of guys who are so good at this stuff that they are kind of, every time they look at a new problem, they create the world's best algorithm in that area. Wow, that's totally impossible to see. Let me try turning the lights off. Okay. So, Google tried something interesting, which was, one of the things is it's very hard to find labeled data, right? It's very hard to find, for example, pictures with something saying this is a picture of. So they tried something interesting, which is that they pointed a deep learning algorithm at thousands of hours of YouTube videos. And they didn't specifically give it any information about what they were pictures of, or even a particular task to do. They just basically said to the deep learning algorithm, try and develop a structure of what you're seeing. And at the end of, so they ran this on 16,000 computers for about a month. And at the end of that, you can basically look at the intermediate nodes in one of these deep neural networks and look at kind of what activates it. One of the node's activations is visualized on the left, and another node is visualized on the right. So this algorithm learnt about cats and about people, and it even learnt that the area around people's eyes doesn't matter very much as to deciding whether they're people, which I guess is it also learnt about eyeglasses. And so this is kind of a really interesting visualization of what happens when deep learning algorithms are just pointed at large data sets and asked to kind of find structures. They actually, when we inquire about what they've learned, it turns out they've learned all kinds of interesting things. So Google actually decided to try and do something with that. So they then took those learnt features and said, okay, well, what happens if we now use them to try to apply that against label data and see whether or not it can recognize some images? And so it started asking this network, for example, show me things that look like a seatbelt, examples in the top left. Show me things that look like a shredder, examples in the bottom right. And so it turned out that this thing that was just trained with this kind of unstructured stream of images, that it actually was able to answer questions very effectively. I say very effectively, that's kind of a lie. An attempt to classify 1 million images into one of 1,000 categories, this is a Boston rocker, this is archery, for 1,000 categories, it actually got it wrong half the time. But that was about 3 times better than previous attempts. Right? So it was pretty good. But it did take 16,000 machines. I will say, however, that this field is moving pretty quickly. When I say it's moving pretty quickly, that was done in 2012. In 2014, it was replicated by one guy running a single computer, his own desktop computer, for 1 week, and he got a 12% error rate. So in a period of 2 years, we've sped this up by 16,000 times and made it 4 times faster. 16,000 times made it 4 times more accurate. So we're now at, and 12% accuracy of recognizing, for example, the difference between different types of dog breeds or different types of mammals or whatever, that's about as good as people do. So again, the speed at which this area of deep learning is moving is kind of crazy. So coming back to this idea of unsupervised learning, what happens if we don't show a deep learning algorithm videos, but instead we show it books? So Google had a deep learning algorithm read 100 billion words of books in a project called Word2Vec. And at the end of this, again, they kind of inquired into the learnt representations and started asking a few things. So one of the things they asked, having had this thing read 100 billion words of books, is, what do you think if I take king and subtract the concept of man and add back the concept of woman, what concept would I get? And Word2Vec correctly said queen. The researchers asked other things like, what would be the Hungarian translation of the word rabbit? And what would be the next thing in this sequence? First, second, third, and it said fourth. And so researchers started asking this trained algorithm all kinds of questions, and it answered all of them correctly. So again, it kind of turned out that getting a deep learning algorithm to look at just a large body of structured data, in this case natural language, that it finds things out. And the weird thing about deep learning algorithms is we don't really know what it's found out until we think of the right things to ask it and the right way to ask it. So I will say that I think we're very much just on the very tip of the iceberg in terms of what's possible with deep learning. So what are the world's smartest people doing with these kind of adventures in machine learning? So one guy I know quite a bit about what he's doing, because I've spent some time with him, is Craig Venter. Craig Venter is the guy who first decoded the human genome. He's the guy that first created synthetic life forms. This is an article about the new startup that he announced a month ago called the Human Longevity Institute. What he's now trying to do is sequence 100,000 genomes and pull together also complete patient histories of all of those people and use machine learning to kind of figure out what causes some people to live long and happy lives. And in the process, try and basically cure aging. So it turns out that now that we, on average, tend to live a long time, the vast majority of the things that we get sick from or die from are correlated more than anything else with just being old. And so, this is an example of someone who has a very good track record of doing things that are meant to be crazy, decoding the human genome, creating synthetic life forms, doing it anyway, this is what he's now working on, and he's doing it basically driven by machine learning. And so, it's kind of interesting how, just to think about what kinds of problems maybe can we solve that we could never solve before. It's also interesting as data scientists to think about what are you working on right now? And if it's not curing aging, what is it? Are you working on something that's really making the best use of your abilities? So, this is something I spend a lot of time thinking about, and, my new startup, I'm going to be spending, hopefully, at least half of my time thinking about these kinds of healthcare and life sciences applications, because these make a big difference. We can also see the impact on, for example, what's going on in Australia. There are now trucks like this one which don't have people inside. So Fortescue Mining has these large fleet of drone trucks. And so we're moving towards a point now where mines, for example, will be nearly totally person-free, right? And so, the Craig Venture longevity example is kind of like things that could change all of our lives very much for the better. This is an example of something that could change organizations' profits very much for the better. They're all going to have a huge impact. And so one of the things I want everyone to think about is, what does this impact mean kind of for how the world is run, right? So here is Australia, coloured in by the percentage of services in employment. So Australia is about 80 to 90% services in terms of by labour force, as is the United States, as is most of Europe. So most of the jobs in the developed world today are in services, right? Now, think about what a services job generally involves, right? So it generally involves reading and writing, speaking and listening, looking at things, integrating knowledge, in order to do these kinds of things, right? So my point is that deep learning is now about as good as humans at most of these things, at least in many areas, and moving so fast that, for example, in the looking at things category, it's about 16,000 times faster in 2 years, right? So what are we going to be doing if not these kinds of things? So clearly there's going to be a big disruption in terms of what people are going to do in the future. It's very hard for us to predict what this disruption is going to look like. Humans get better at stuff at kind of, some kind of linear-ish speed, I guess. I believe machine learning and probably things that are derived from deep learning, at the moment they're getting better exponentially, quickly, right? And I think that'll continue to happen as we give them more computing power and more data. There are no known limits on how they can use that, right? So this would be the equivalent for kind of computer performance. Now, I started using neural networks the first time about 20 years ago, when they were kind of down here, right? And they were pretty disappointing on the whole. Apart from anything else, I was working or doing some consulting with Westpac at the time. The system cost them about $15 million. It certainly didn't pay its way back. Right now, we're probably about here. So right now, we're still at a point where a lot of the time you try and apply machine learning to something, you end up with this kind of slight disappointment, particularly if you don't necessarily quite know what you're doing, or particularly if you're using stuff that's embodied in off-the-shelf software products, because the cutting-edge stuff I just showed you out of academia doesn't yet exist in the stuff that you can download and buy, right? So kind of, we're here, right? So maybe this is 2 years' time, and maybe that is 2 years after that, right? So it's very hard for us to understand kind of how exponential growth affects what computers can do or what machine learning can do. And, I don't know how many years this is or how many years this is. This is more a conceptual thing, right? To say, I think we'll all be surprised at how many jobs computers will be able to do better than us in the coming few years. So, this kind of displacement has happened once before in human history. In the Industrial Revolution, we basically, in fact I'll show you the next slide, this is what happened. We basically had a point where productivity was pretty low because the vast majority of humans were either inputting their own energy into processes or were like driving horses and oxen and stuff like that and inputting their energy into processes. So about 80 or 90% of employment was kind of in agriculture and stuff like that. The Industrial Revolution came along and the steam engine was invented, and the steam engine replaced all of those people with the power of steam to create energy, and so suddenly energy was being taken not from the people and the horses and so forth, but from engines, and so we had a huge increase in productivity until we got to the point where, everything that could be enginized had been enginized, and then we kind of flattened out again. So there was this step change in productivity because of the creation of the engine. Now, as a result of that, there was a lot of displacement. A lot of historians believe that for decades afterwards, most workers were worse off. There was a lot of poverty, a lot of social strife, even although at the end of it, none of us would want to go back to pre-industrial revolution. We kind of eventually found new ways of getting people to work. So this is the same chart as last time, I've just changed the scale. Right? And the difference with the machine learning revolution that I'm predicting is that I think it looks like this, which is, it's not a step change, but I actually don't think there's any flattening out. Like, okay, you could get to the point where machine learning algorithms are doing all the intellectual work that people currently do, but it wouldn't stop there, would it? Right? I mean, they would get better at doing that intellectual work. So, I foresee a larger social and economic implication from this machine learning revolution than the industrial revolution, by a lot. So this is both kind of exciting and scary, right? I mean, potentially if computers do all of our jobs for us, then that means we don't have to go into work tomorrow, and well, we all probably have interesting jobs. The vast majority of the world, does things like food preparation or cashiers or, jobs that if you said to them, would you like $500,000 a year to not work, they would say, yes, I will, and they would, practice surfing or violin or write poetry or whatever, right? But at the same time, of course, the problem is at the moment that we pay people based on their labour input. And so we can already see this problem happening. In the last, 25 years or so, productivity, which is the blue line, has continued to increase. However, this line here, which is the value of labour, as represented by median wages, has been flat. And in fact, in the last few years, it's been dropping. This is exactly what we would expect to see if this is true, if in fact the value of human labour is becoming less important and that there are large numbers of people in the world who have jobs that are now better done by machines. So there is some empirical evidence that this is happening. Okay, so how am I going for time? Great. So I won't cover these. That's fine. So that's kind of the reasons I'm excited about deep learning, but the reasons I'm slightly scared about deep learning talk. Maybe I'll just mention this last slide. What are the things that could help us deal with this disruption, right? So often people will say, oh, let's invest in education. So what happens when you invest in education? When you invest in education, you get more people that are probably going to be better at training the computer algorithms to do a better job, and as a result, you make the curve shift up faster, causing a larger income disparity and more people who can't add economic value. So that's actually kind of a short-term solution for the people who are educated, because they'll be the last ones whose jobs are lost, but overall, it doesn't fix the overall problem. Another is, oh well, you know, if half the labour force isn't working, it's because they're all lazy, so we just need to give them more incentives to work, so let's remove their health care and the dole and, you know, get them so that they actually have a reason to work. And of course that doesn't work either, because if like half of the workforce can't add economic value because computers are better at doing their jobs than they are, incenting them by making their life miserable if they don't work just makes them miserable. So, step one could be a negative income tax, which means that even if your job, you're less good at it than the machine is, if the government will pay you $1 for each dollar you earn, then you're actually getting rewarded enough that it's still worth you working. So that's something that Milton Friedman came up with in the 50s. This is not a new idea by any means. Switzerland is currently talking about a basic living wage, which is giving everybody enough money to live a dignified life, regardless of what they do, and regardless of who they are. So a basic living wage would allow everybody who has not found a way of adding economic value to still live a dignified life, and then they can spend their time on whatever they most want to. Remembering that, as a result, we don't have a problem, we're not trying to create more incentives to work. We're trying to stop a situation of having a huge underclass. And hopefully, if we deal with all that effectively, we actually end up at the point where we don't have scarcity anymore, and then none of us have to work, and we can spend all of our time going to meetups. Or, you know, if you'd rather do something else, I guess that's okay too. So, I don't really have time to tell you much about technically how deep learning works. So, maybe I'll try and tell you a little bit about it, as best as I can. Phil, how long do you want at the end? 15 minutes? Okay. I'm not even sure if this is going to make sense, but we'll have a go. All right, I'm going to teach you about how word2vec works, right? So remember I mentioned earlier word2vec. Hello? Oh, there we go. Word2vec. So this is this thing that Google did where they kind of had a deep learning algorithm read 100 billion words of books and kind of then asked this network all kinds of interesting questions. What did it actually do? And so I wanted to describe to you what it actually did and why it does things that are kind of interesting. So when we want to take a sentence, so in Google's case, they took each book and they split it into 11-word phrases, right? So words 1 to 11, words 2 to 12, 3 to 13, and so forth, right? Now, you have to feed that to a machine learning algorithm. Machine learning algorithms in general expect floating point numbers, not words, right? So the floating point number is like, 1.036 or whatever, right? So in general, an algorithm expects a whole bunch of these numbers. So how do we take a 11-word phrase and convert it into a bunch of numbers? So the Google guys did it in the most naive, stupid way you could imagine. They basically said, okay, English has about 170,000 words in it, right? So here's like 170,000 numbers, right? And the first word of this phrase is the, right? So what we're going to do is we're going to decide that the word the is word number 380. So they go over to word 300, they go over to the 380th element of this array and they set it to 1 because it's the, and the is word number 380, and they set every single other number to a 0. right? And that's how they encode the, right? And so the second word in the phrase might be machine, right? Machine is word number 4009. So they find the 4009th number in this next section, and they set that to 1, and they set everything else to 0, right? And so on and so forth until they have 11 times 170,000 numbers that represent this 11-word phrase. And of course, in that 11 times 170,000 numbers, 11 of them are 1, and the other 11 times 170,000 minus 11 are 0, right? Now, that sounds like a weird way to do it, but regardless of how weird it sounds, you have to agree it at least does it, right? This is our way of converting an 11-word phrase into a bunch of numbers. Now, they then have to create like an output. So anytime you use machine learning, there has to be something you're trying to do. And so what Google did was they took every 11-word phrase from these, what was it, 10 billion, 100 billion, whatever, words, and they repeated every phrase twice. And for every second time it appeared, they took the middle word and they replaced it with something totally random, right? So as a result, you had, 10 billion times, so how many that would be? So, X billion correct 11-word phrases and an equal number of incorrect 11-word phrases where the middle word was replaced with some random garbage, right? And so what they tried to get the algorithm to do was to spit out a 1 in the cases where the middle word was was right, and a 0 where it wasn't. So effectively they were trying to get this network to recognize well-formed phrases, right? So the interesting bit is what happens in the middle. And so the interesting thing about deep learning networks is, and so anybody who hasn't done any neural networks here may find this goes a little bit too fast. We'll see how we go. What we do is we do some very, very, very simple linear algebra. We basically take each of these zeros and ones and we multiply each one by a weight, right? And initially that weight is totally random. So this weight might be 3, right? So we go 0 times 3. This weight's random, this weight's random, this weight's random. So we multiply each of these things by some random weight and then we add them all up to create some number. We call this a hidden node in neural networks, right? And we do this again with a different set of random weights to create some other number. And we do this lots and lots of times, right? So in here, there's like lots and lots and lots of weights, right? Now the interesting thing is, this thing in the middle here only has 1,000 numbers in it, 1,000 hidden nodes, right? Now we then basically do that a whole bunch of times. So we take these 1,000 and we again multiply them by some weights and add them up. And we do it again with some new weights and we multiply them and add them up and so forth until eventually the very last group gets multiplied by a final set of weights and added up. And we find out whether that thing is greater than 0 or less than 0. If it's greater than 0, we say, okay, that's a well-formed sentence. If it's less than 0, we say it's not a well-formed sentence. Now, I'm just telling you what it is, and then I'll try and tell you why, right? Initially, all of those weights are random. So initially, this is wrong as often as it's right at deciding whether or not something is a well-formed sentence. And this is why now we have to use, remember I told you, you need to use optimization in linear algebra. So multiplying things and adding them up is linear algebra, that's just a matrix product. And doing optimization is stage 2, which is basically figuring out what are the weights in this network which maximize the number of times that this thing that decides whether or not something is well formed is correct, right? And so we do that using a very, very simple algorithm where we basically feed in these through the random weights, we find out how much it's wrong by, and then we basically subtract that from all of the weights. And we do that for every row, and we do that lots and lots of times. And it turns out, so this thing is called, doing that is called stochastic gradient descent. And it's basically the world's easiest, simplest, most stupid optimization algorithm. You can write it in about 15 lines of Python. Particularly because NumPy is going to handle all of the matrix algebra for you, right? And so that 15 lines of Python is pretty close to the best known way of optimizing these deep learning neural networks. So at the end of all this, you're going to end up with a whole bunch of weights, which, when you feed in these 11 times 170,000 numbers representing a sentence, will do a good job of telling you whether or not that sentence is well formed. That in itself is not useful particularly, but what is interesting is that somewhere along the middle, that entire 11 times 170,000 words got compressed down, numbers got compressed down into just 1,000 numbers. Sorry, this is not quite correct. It got compressed down into 11 lots of 1,000 numbers. So in fact, all of these go to the first lot, and all of the second go to the second lot, and all of the third go to the third. So 11 lots of 1,000 numbers. Now, because this first layer never was attached to any of the later layers, right? It's only attached to the layer immediately above it. That means that all of the information necessary to decide if a sentence was well formed must be available in this 11 times 1,000 numbers. And that means that for this network to have worked, it must have found a way to represent every word in the English language effectively with just a vector of 1,000 numbers. And that is actually what word2vec does. That's why it's called word2vec. It takes a word and it spits out a 1,000 dimensional vector, which somehow within it contains all of the meaning of that word. How did it do that? We actually don't know. We actually don't know how it's been encoded. All we know is that it has, and we know that it has because it's doing a really great job of deciding which sentences are well formed and which ones aren't. Right? All we know is that somehow it's done it, right? And then we can start to ask questions about this representation. So given you found a way of representing all of the nuance and subtlety and meaning of every word in English with just 1,000 numbers, let's start asking it questions. So if you remember the thing I did before of queen minus woman plus man, what we actually do is we take the 1,000 dimensional vector for queen. We do an element-wise subtraction of the 1,000 dimensional vector for woman. We add the element-wise add the 1,000 dimensional vector for man. We end up with some new 1,000 dimensional 1,000 element vector. We then basically do a k nearest neighbours, or I should say a 1 nearest neighbours, to find what is the one thing in a 1,000 dimensional space which is the closest, and that's the thing that turns out to be queen. So when people, for example, the one which was like, how do we translate English to Hungarian, you can basically look in this 1,000 dimensional space and find out in what direction can I go and how far do I go to convert a word from English into Hungarian. And it turns out there is a particular vector and a particular distance that has found that. So basically it turns out when you look in this very complex space that all of this nuance of language has been kind of embedded. So that Stanford sentiment analysis parser, right, the way that actual parse tree is built is basically by combining pairs of these word vectors together and finding pairs which kind of make sense according to this model, and that's how it can automatically parse a sentence. And so then you can actually combine these 1,000 element vectors together up through a parse tree, and you end up with an 1,000 element vector representing a whole sentence. Right? So if you remember the thing that compares, says, for these images, which sentences are the best sentences? Actually what it's doing is it's doing the equivalent of word2vec for an image. So there's basically an equivalent thing you can do for images to create a vector version of the image. It's doing the same thing for the sentence, and it's basically then saying, let's just find the nearest vector, because they're now just numbers. Right? So what deep learning's doing is it's turning all of this kind of unstructured stuff, pictures and videos and molecular formulas and sentences and so forth into the same consistent representation, which is this vector representation. And so these vector representations are called distributed representations. There's a question in the back?
Did they come up with that 1,000 element vector randomly or through trial and error or
It's through optimization. So the way that 1,000 element vector came up was by creating a neural network, like the one I've shown on the screen here, putting in random weights, right? And then having a whole bunch of layers of these. So it goes multiply, add, multiply, add, multiply, add. Well, actually also in the middle, it's not just multiply, add, it's multiply, add, and then something called an activation function, which for those of you who do have some background in statistics will generally be a logistic function or a rectified linear function. And then using this thing called backpropagation. And backpropagation is just a very simple type of optimization algorithm that finds the weights which are the best at doing this thing of deciding whether something's a well-formed sentence. The 1,000 element vector is just a handy outcome from the fact that these layers in the middle have a lot less numbers in than the input layer. So basically, the algorithm automatically figured out this representation. So it's kind of trial and error, but it's a very specific kind of trial and error.
So you could type optimization mostly to minimize the
No, the length of the vector is fixed. So this is one of the tricky things with deep learning and neural networks in general is how many hidden layers and how many nodes in the hidden layers and what activation function and blah, blah, blah are all things you have to decide ahead of time. So the only thing the optimization algorithm does is to decide what each weight is, what the number of that weight is. So the way people decide how many nodes and stuff like that is they generally build a few different networks and find out which one happens to work the best. In this case, it turns out that about 1,000 elements seems to capture the vast majority of the richness of human language.
So is that essentially related to micro one way too many
So this is actually not quite related to over and underfitting, but it's a really good question because it leads us to a very interesting topic. So Geoffrey Hinton, who kind of invented this topic, says the whole point of neural networks is to overfit. The whole idea is to have so many parameters that it can match any kind of underlying functional form that you require. The trick is then to somehow deal with the overfitting. So the way that we deal with the overfitting is through a number of things. One is to just use so much data that it actually only sees everything once, right? So in Google's case, they have the entirety of Google Books, right? So it actually, in its stochastic gradient descent, it actually only sees each phrase once. So it can't overfit when it only sees it once. For stuff like learning about images, people tend to add random noise to the image, they'll reflect them in one axis, they'll move them around a little bit, they'll change the lighting, and so forth to kind of create more data. Then there's another thing really important called dropout. And dropout is kind of where random forests and neural networks meet. Dropout is something where each time you are doing a backpropagation stage, so each time you're training the weights to get a bit closer, you randomly throw away half the nodes. And when you randomly throw away half the nodes each step, it's impossible for the network to kind of overfit because suddenly the network's different to what it thought it was. So we actually intentionally create a network with way more parameters than it needs, but then we use various tricks to make sure that it can't actually overfit with those parameters. Yeah?
Could you point out again the exact point at which the word order is learned by this?
Yeah, so the word order is the word order is explicitly defined by the input vector. So let me draw this out. So if we've got a sentence which is something about machine learning is really blank. And we want to turn this, and there's 11 words in this phrase, we want to turn this into a bunch of numbers, right? So what we do is we basically create a vector containing 11 times 170,000 numbers, a single vector, right? And the first 170,000 numbers we set to all 0, except we take the word machine and we look up machine in some kind of table to find out machine is what number word in the English language, right? So it turns out it's number 70,001, right? So we basically go and we find element number 70,001 and we set it to 1, and all the rest is 0. So we do that for each word of these 11, and then we just stick them all together into a single 11 times 170,000 element vector. So the position of the words is explicitly there because that's in the position in the vector. Yeah.
If you had a data set where you look at the data of the words and realise there was only, say, 50,000 relevant words, could you then change the corpus and use that?
Yeah, absolutely. Yeah.
Would that make sense to optimise the performance things?
Yes and no. I think the issue is if you wanted to use a smaller vocabulary, then you get to use less sentences from less books, right? So in Google's case, I guess they decided, this is the vocabulary size that they're going to use. I don't know if they tried, like you could, for example, decide to use 50,000 word vocabulary and anything not in the 50,000, you could just change that word to foo or something. I don't know if anybody's tried that. I don't see why that would help though, because that kind of implicit compression that gets done when it gets stuck into a 1,000 element vector, ought to be able to identify that some words aren't very common and that they don't need to worry too much about finding their meanings, I guess.
How would that work for something like Chinese where it's bigger than that, right? Would you have a bigger vocabulary?
Well, Chinese actually isn't bigger than that. There's, 6,000 Chinese characters in somewhat common use, and the number of words that you can create that are used in the two pairs is actually similar. They're similar size. Chinese bigrams are similar. So I actually believe English might be the language with nearly the largest number of words. So I'm not sure it's actually a problem. Yeah.
So for deep learning, you mentioned that you need a lot of computing resources.
Yeah.
To run it well.
Yeah.
So do you know if the guy who won the first Kaggle competition using deep learning, he used his personal computer? Or?
Yeah. Okay, that's a really good question. So here's what happened, right? I said that the big Google YouTube watching cat detecting thing took 16,000 computers. And then 2 years later, a much better algorithm was done on one computer. The key is that we figured out how to use GPUs. So GPUs are the cards in your computers which are designed mainly for running games. And it turns out that basically games involve a whole lot of linear algebra. So these GPUs can do about 2,000 operations at a time. So basically, once people figured out how to make GPUs run neural networks extremely efficiently, they immediately had these things running, basically 1,000 times faster. So yes, nowadays the vast majority of real-world deep learning is done on single machines, but very often using multiple GPUs. Mainly on 2 GPUs at a time. But about a month ago, a new paper came out describing how to do things on 8 GPUs at a time at a performance increase of 6 times doing just 1 GPU. So we seem to be kind of hitting the sweet spot around doing real-world image recognition and natural language processing on a single computer, but we're still at a point at the moment where it takes a few weeks to do these really big problems. The good news is that if you guys get interested in deep learning, you probably won't have to train a deep learning algorithm yourself. Now that people have actually created these distributed representations of images and of words, you can basically download those for free off the internet and use them directly. So you can go to Google's Word2Vec webpage and download the 1,000 element vector for every one of 2.5 million concepts So not just English language words, but also people's names and place names and so forth. And start to just use them. And then there are similar things for images. So my students in America, I had them enter a Kaggle competition called Cats versus Dogs, where they had to figure out which images out of about 50,000 were pictures of cats and which ones were pictures of dogs. About 2 years ago, there's no way that anybody in that class could have got more than like 51% correct. I mean, that's a really difficult problem. But in my class, they were able to use a pre-trained neural network, which had already been trained to recognize over 1,000 different types of objects and basically customize that a tiny little bit. The existing weights and everything worked just fine. And in my class, the person who got the best result got 95.4% correct. And this is a bunch of first year's master's students, basically. So, we're at a point now where most of that computing has actually already been done for you.
But even for that, you still even this one in matrix, I bet you still need very big matrix, like 100,000 multiplied by 1,000, so feet to the right.
Yeah, that's right. So so if you download this, it's called the ImageNet. So if you download an ImageNet pre-trained neural network, it's going to be 5 or 10 gigabytes. It's big-ish. But a friend of mine actually created a version of that which runs on an iPhone. So you can actually get it down into a pretty good size. So if you Google for Deep Learning SDK iOS, you'll find something by a guy called Pete Warden, who actually has a cat detector running on an iPhone, and he's got a really cool video showing this thing that he's built, which as he points his video stream at objects, the more cat-like they are, the faster it beeps. So, we do actually have these things running on pretty small devices now, which is quite impressive. Okay, cool. So I've got a few more minutes. I think I've told you as much as I want to about kind of how deep learning works. I think my main messages about it, for those of you who are interested in taking this further, is to say it's starting to actually get quite accessible now. If you can't code, you can't do deep learning right now. Like, it's just not something which is totally out of the world of research. The libraries that are out there are research quality libraries, but they also don't require you to be an expert. I mean, I'm a very bad mathematician myself, and I can use these things reasonably well. And if you don't have a GPU on your desktop computer, because you probably only have a laptop and that probably doesn't have a separate NVIDIA GPU, you can, for $1 an hour or something less, hire from Amazon. They have GPU-enabled instances. So it actually is pretty easy to get up and running. A good place to start would be either look at the Kaggle Cats and Dogs competition. There's a lot of great forum threads there where people basically came onto the Kaggle forum and said, I have no idea what I'm doing, somebody tell me step by step, and people have written blog posts saying, here's how to get a top 10 finish in this competition end to end. Another example was another competition that just finished called the Galaxy Zoo competition, which was astronomical object detection. That was also one with deep learning, and the guy who won that also wrote a really clear, simple blog post, step-by-step instructions, and all of his code is on GitHub. And that takes about 3 days to train on an Amazon instance, but you could always do it on a smaller data set in a couple of hours. I think no one really knows yet whether this is kind of going to totally take over. As I said, really in industry right now, it's all about, or it's becoming all about random forests. That's definitely the kind of the go-to algorithm for me if I actually want to get real work done at the moment. But there's a reason that I'm teaming up with one of the world's top deep learning experts in my next startup, which is I do think it's going to be the future. So if any of you guys start playing with it, feel free to reach out to me. I'll write my email address here. It's just j@howtocode.com. howard.fm. Yeah, did anybody have any other questions about, well, anything you like? Yes?
Initially you said that deep learning does not require an additional hypothesis as opposed to other machine learning algorithms. Isn't that additional hypothesis what makes most of the work and value of a data scientist?
Right, I don't think I said that, because that's certainly not quite what I think. I did say that a couple of interesting examples of deep learning came from something which is kind of more akin to compression, right? So Word2Vec has created something really powerful and useful, not because they tried to solve a specific problem, but just because they tried to create an architecture that could recognize well-formed sentences. Now that they've done it, we can take the results of that work and use it to answer real-world problems, like how do I summarize this web page into 3 sentences? Or how do I recognize all of the documents that are about this same topic? Or, you know, Google image search uses deep learning to find, find all of the images that are images of cats. So yeah, I mean, I'm actually a huge non-believer in unsupervised learning in general. I think that all of the interesting work is done with supervised learning, i.e. you decide what it is you're trying to do. So it's not data mining exactly, but it's like, okay, I'm trying to find which customers are likely to crash their car and have high insurance claims, or which customers are likely to be interested in this product if I recommend it on this web page, or so forth. So yes, I do think that the value of machine learning comes when you have a specific problem to solve and you customize the work based on solving that problem. Great. Okay, well, one more. Yes?
What methods are out there to turn like a pack of images into sort of numeric data?
Well, it depends. I mean, so pixel data is one thing, other numeric data is something else. So all banks of images are pixel data by definition, right? So, I mean, compressed perhaps, but it'll be one line of Python to turn that into actual RGB color values. What you really want to do is something like what Word2Vec does with words, which is to turn it into a bunch of numbers where things which have similar bunches of numbers are pictures of similar things, right? So that's what we'd call a distributed representation. So there's a few great libraries for doing that, and I'll just write them down here. So there's Overfeet, there is Caffe, there is Decaf, and there is libccv. These are libraries which basically are effectively pre-trained neural networks, and if you feed an image into it, it will spit out a few things. It will spit out something saying, I think that's a picture of a cat, for example, and it will also spit out something basically which is, here is a 1000 dimensional vector which somehow encodes its catness and that it probably has 4 legs and that it's fluffy and it tends to be in indoor scenes and blah blah blah. And in general, it's a bunch of numbers which you should be able to feed to other algorithms and get really useful results from. Is there a part of you that's bothered by it? No, not bothered by it. I mean, more intrigued by it. I like exploring spaces we don't understand. So I'm most interested working on things where the problem is unsolved, particularly where there's things going on that seem great but we don't know how they're happening. So I find this a huge opportunity. I don't think we'll ever totally understand it because it's we're starting to approach, not quite, but we're starting to move in the direction of kind of levels of complexity up towards the human brain. I mean, the human brain has 100 trillion connections. The largest deep learning networks have 1 billion connections, so we're still many orders of magnitude short. But, we shouldn't expect that when we create an algorithm that's specifically designed to learn from experience, that once it's learned from experience, we shouldn't expect that we could then say to it, tell me exactly what you've learned. You know, I think that's reasonable. Yeah.
That is what we expect of other people. When we want to gain their credit, make sure their credit will trust their ability to explain that.
Right, so we don't ask from people which neuron connections fired and why, right? We ask them from their hierarchy of concepts, how did they get combined to kind of come up with this answer? And these are the kinds of things that people are interested in and I'm certainly interested in starting to ask neural networks about. So there's some interesting work done recently on trying to visualize the intermediate layers inside neural networks and find out what have they really learned, and when they're solving a new problem, what are they really doing? But yeah, we're still kind of in the early days of that, but we shouldn't assume that we won't be able to make any progress there. I think actually we will.
Is it possible in the next few years that we'll have computers actually making decisions in regards to social interactions for us, like who to work, who to meet, so forth?
Oh, I mean, they already are, right? I mean, so like OkCupid had this great blog, right? They had a good data science team. They're you know, I don't know if they're in Australia or not, but at least in America, they're one of the most popular dating sites. And yeah, I mean, they genuinely were using algorithms to suggest who to meet. This is actually something that computers are probably already better at than people, because people like, I don't know if you guys read the book Predictably Irrational, Dan Ariely, fantastic book, right? He's a researcher who has done a lot of research into all of the ways in which human brains are, you know, systematically biased and explicitly consistently wrong, right? The good thing about computer algorithms is that they're explicitly trained to not be biased, you know. So I actually feel that using algorithms for that kind of thing is a really very good use of it.
Question about your prediction for the machine learning revolution. So, as you said yourself, 20 years ago, neural networks had already been around for a long time, and it was a big disappointment.
Right.
In general, there was disappointment for machine learning and AI. So, why is this any different? Is it just that we have hardware to do this?
Yeah, I mean, it's basically because it's basically because of this, right? I mean, here's 1980. We couldn't store much data. Not many people stored data anyway, because it was like the stuff wasn't online. We didn't have much computation speed. We didn't really have GPUs for general purpose computation. So, you know, we were in the trough of disappointment. So yeah, we've got better. And the thing is, as the computers have got better and the data's got bigger, and we start to be able to solve more real problems with neural networks, suddenly then more researchers start coming in. So like after my friend Richard Socher started like killing NLP problems with neural networks, suddenly now when I go to academic conferences, NLP researchers come up to me and they say, I've been spending 20 years doing like, you know, LDA for topic modeling, should I be doing neural networks? So as we come up this curve, it actually attracts more and more great minds into this approach. So we not only have the data and the computation, but also we actually get more and more top people. You know, last time I was doing a tech talk in Melbourne, I wasn't talking about deep learning. But now, you know, maybe some of you will go away and think, oh, maybe I should start learning about this for what I'm doing. So I think it'll keep feeding back. You know. Great. Okay. Thanks very much.